Yellow light of photon energy 3.5 times 10 to the minus 19th joules is incident on the surface of a particular photocell. Calculate the wavelength of light, right? So just use your, what wavelength is hc over E. And they've given it to you in joules, so, you know, you use the hc that's in joules, right? Electrons emitted from the surface of the photocell have almost no kinetic energy. Okay, so here's what they're saying, right, is that this energy is the work function of the metal, right? Okay, and that's why it doesn't contradict conservation of energy, right? Is that, remember, the photon energy, that's not PE, not potential energy, but photon energy turns into work. What's left over turns into kinetic energy. This is just conservation energy. This is the total energy you have. It goes to the work function, and what's left over goes to kinetic energy. Since they have no kinetic energy, that means that it's just equal to the work function, okay? So I think we're good there, right? Okay, radiation of photon energy 5.2 times 10 to the minus 19th joules is now incident on the photocell. Calculate the maximum velocity of the emitted electrons, right? Well, 5.2 times 10 to the minus 19th turns into the work function is, that's what they're saying. When they say they have almost no kinetic energy, then those photons are equal to the work function, right? So that's going to be 3.5 times 10 to the minus 19th plus the kinetic energy. So figure out what the kinetic energy is, and then just use the formula for kinetic energy is 1/2 mv squared. The mass you look up in your data packet will be the mass of the electron, okay? All right, so yeah, there we go. I got this one wrong, actually, because for some reason instead of 5.1 I used, or 5.2, I used 5.1, which is just odd, you know? All right. Don't know why I used a different number. All right, let's see. Photocell is connected to a cell as shown. The photoelectric current is at its maximum, the saturation current. Okay, so notice that normally we hook up a cell and we're trying to stop those electrons so we can measure their kinetic energy. Notice that now we've made this side positive, right? Okay, and we did that as well with our little simulation, right? Well, when you make that positive, anything that's emitted from the surface definitely leaves the surface. It doesn't go back. It's like, whee, it accelerates across, right? Okay, so anything that gets ejected from the surface definitely goes flying across, right? And then notice that that we've got an energy bigger than the work function for the light. So every photon of light that comes and hits is ejecting an electron, okay? And so the current is proportional to the intensity, or the number of photons, sorry. Okay. The current is proportional to the number of photons that you have. Every photon emits an electron, and every electron goes flying across because we've made this side positive. Okay, so let's see. Radiation with a greater photon energy than in B, right, so greater than the 5.2 times 10 to the minus 19th that we just figured out, right, is now incident on the photocell. But the intensity of this radiation is the same as in B. There we go, right? Well, remember that intensity is watts per square meter, right? And a watt is a joule per second per square meter, okay? Well, what this means then is if we now, let's say, so what they're saying is they're going to go from, say, blue light to violet light or something like that, right? Okay. If they go from blue to violet light, but the intensity stays the same, remember it's the same number of joules in a given second, right? So, and if every photon has more energy, but the energy is the same, you're going to have fewer photons, right? Okay. Each photon has more energy now, right? So for the same watts per square meter, you'd need fewer photons. Okay, that is, by the way, the correct word. You would not say less photons because photons are discrete objects, okay? You'd say fewer days, fewer people, right? Less humidity, right? We can't count humidity, right? Anything that's discrete and you can count, sorry, English lesson, right, would be fewer. So there'd be fewer photons. That's because that's the joules are the same, but each photon has more energy, so you need fewer of them, right? Okay, so the number of photons per second would be fewer, right? What would happen to the current? Well, since every photon ejects an electron, and since the current is made out of electrons, right? And you have fewer electrons, what does that do? Yeah, make an argument, right, for what that would do to the current. Okay. You need to make the point, though, that there's a one-to-one correspondence between photons and electrons. If you have fewer electrons than that, well, then that'll affect the current, won't it? Okay. All right.